So my name is Matthew Peters. I am a research scientist at the Allen Institute for Artificial Intelligence. For those of you who haven't heard of us, we commonly go by AI2. We're a nonprofit AI research center based in Seattle, Washington, and we are funded primarily by the late, great Paul Allen.
Can you tell me a little bit about the goals of the organization?
Sure, we have a pretty broad-based goal, which falls under the overall umbrella of doing artificial intelligence for research for the common good. So that's sort of our broad-based mission. Most of our work is open source, and we publish all the research that we do. We focus primarily on language understanding tasks, getting computers to understand language in a way that humans do, although we also have a very large and active computer vision research team.
And I asked you on to talk about the ELMo paper, of course, but before we get directly into it, could you tell me a little bit about your background and what led up to that line of inquiry?
I have formal training as a PhD student. I got a PhD in applied math from the University of Washington. During the course of my PhD work, I studied a lot of numerical computation methods. In particular, we were interested in climate modeling at the time and doing large-scale data analysis. Then from there, I went and worked in the finance industry for a while doing mortgage modeling and transitioned into the tech industry where I did machine learning product development and led a machine learning product development team for a local startup here in Seattle, and then transitioned into my role as a researcher here at AI2. The initial motivation for working on the ELMo project was the first original team I worked on at AI2 when I started over 2.5 years ago now was the Semantic Scholar team. And in particular there, we were interested in solving language understanding problems for data sets that we had very little human annotated data for. In particular, we were doing information extraction from highly technical scientific articles like peer-reviewed publications in computer science or neuroscience. And gathering annotation was very hard and very expensive. And so I was highly motivated by looking for ways to do state-of-the-art NLP with very little human annotation. And so that was sort of motivation for working on ELMo.
So on the show previously, we've talked about Word2Vec and just some of the basic high levels of embeddings. Can you talk a little bit about where ELMo falls into the landscape of things there?
So that's a great jumping off point is Word2Vec. And when we started the project, as you probably discussed previously, Word2Vec is a method for representing input text in a way that we can run machine learning algorithms on it. And in particular, it assigns each word a unique vector. But this is independent of the context. And so in particular, in the Word2Vec setting, a word like bank or play, these are English words that have many different word senses, and the sense of the word is dependent on the context. In one case, I might be talking about the financial institution, a bank, or in another case, I might be talking about the area of land next to a river. You can't tell which meaning of bank you're referring to until you have, say, the entire sentence or paragraph in which the word is used. And so this was the initial intuition for ELMo is that, well, let's learn really high-quality word vectors, similar to Word2Vec, and in a similar manner from lots and lots of unlabeled data, but let's do it in a way that's context-dependent, where in the end, when I want to compute a word vector for the word bank, I don't just use the fact that it's bank, but I use the entire sentence or paragraph in which the word appears in order to say, oh, okay, I actually really mean this particular meaning, this particular sense of this word.
What is ELMo useful for? Why would someone adopt it?
It's useful for a very wide variety of different NLP problems that we solve in practice. An easy way of saying is any place where you'd use Word2Vec, you could use ELMo. When we started the ELMo project, almost every single state-of-the-art NLP system, it's not every single one, but many of them first start with pre-trained word vectors at some point. Word2Vec or Glove is a very popular one that people use for English. And then they build their supervised NLP systems on top of these. And these would do tasks like text classification. So here I'm given an input of text and I want to categorize it. Maybe I want to say whether it's positive or negative sentiment. These are tasks like information extraction, where maybe we're given a news article and I want to extract all of the different people and organizations and other named entities from the text and how they relate to each other. There's tasks like question answering. Maybe I'm given a paragraph from Wikipedia and I want to be able to answer some question about it. And various other NLP tasks that are very useful in building practical applications. All of these systems at the time used Word2Vec or Glove as sort of the input, and then they had their additional architecture that they train on supervised data on top of that. And so every one of these is a case where ELMo would be useful.
And what makes ELMo ELMo? What are its qualities in terms of the structure of the network architecture and things like that?
So the key components of ELMo are training on lots of unlabeled data using a language modeling objective function and a neural network architecture that is suitable for doing language modeling. Language modeling is an NLP task where a model is asked to, in the traditional sense, given a partial context fragment, predict what word comes next. You might have a sentence like, the people were walking down the street and then they. And then the model needs to predict, okay, what word comes after this partial sentence fragment. That's language modeling. Because it doesn't require any explicit human annotation, you can train it on very large amounts of unlabeled data. And then what we did for ELMo is that we took a language model. In our case, we actually took two different language models, one that worked in the forward direction where it reads the partial sentence fragment and predicts the next word. And then we have one that works in an analogous manner, working in the backwards direction where it'll start from the end of the context and work backwards, then try and predict the previous word. And these are trained on lots of unlabeled data using a state-of-the-art neural network architecture for doing language modeling at the time. The internal representations that the language model learns in the process of learning how to do this task are then extracted and used as our contextual word vectors, as our ELMo vectors. And this is what then gets ultimately used in these supervised NLP tasks, like I talked about, this question answering task, for instance, if you're interested in that, as a replacement for the Glove or vectors or the Word2Vec vectors that were there previously.
So one of the strengths of ELMo, or at least the models you've trained, is the corpora you've built it on and the size of that. Could you talk a little bit about what your training corpus is and how large of the data you're able to process?
These methods are very scalable. You can train them on very large corpora. The corpus that one chooses in practice should, in most cases, be motivated by what their end tasks are. In our case, we were interested in sort of a relatively wide variety of different NLP tasks. We didn't have any one in particular that was, say, for instance, a very domain-specific task, like, oh, I want to do information extraction for, we'll go back to the Semantic Scholar example, for, say, research articles or something. In our case, we just wanted to process just general domain data. And then for the ELMo paper, we just chose a benchmark data set, which was essentially news data. And we did this because we wanted to compare our language model implementation versus other large-scale language models that had been trained on a similar benchmark data set. Of course, subsequently, since we published the original paper, people have trained ELMo models, ourselves included, on lots of different data sets in order to get a model that is more particularly suited for a particular application, say PubMed articles or other sorts of specialized domains.
From like a DIY perspective, what is the intention of AI2? Do you think people are going to follow the research and build their own models from scratch or pick up the models you've released? I guess, yeah, what do you see as the way someone can get their hands dirty with ELMo?
So it depends on who you are and what your end goal is. And people have used the Pretrain ELMo models and code for a wide variety of different things. Of course, there's the research community. These are people that are looking to build state-of-the-art systems, and they might want to use, say, the best available technique in order to make their system as good as they can. There's definitely commercial applications. For instance, if you were building a commercial NLP application, you might consider using ELMo to improve the quality of the models that you already have, which might use Glove vectors or something like this. So those would be the primary applications.
And for someone who's looking to just pick up the pre-trained models, can you talk about the process from day one to delivering something?
The pre-trained models, we have them available in a couple of different places. They're available. We have open source code via Allen NLP, which is a open source library that we developed here at AI2. And this is written in PyTorch. So if you're using PyTorch for your deep learning infrastructure now, then this would be a good choice. There's also available in TensorFlow. In particular, they're actually available in TensorFlow Hub, which is a central repository of supported public models that TensorFlow itself supports. So you could get the ELMo's model via TensorFlow Hub. So if you use TensorFlow, that'd be a good choice. And then what you would do is to integrate it into a final product. If you have an existing model now, an existing annotation, maybe you have something that's in production or something that's in development, then you can integrate ELMo into your existing model that you have. Let's say you have something with glove vectors, then you could substitute it for your glove vectors. If you don't have an existing model, if you're just in the starting process of developing an NLP application, then you're going to need to do the standard things like collect data, define your task, and so on and so forth before you could use ELMo as part of your final trained machine learning system.
All right, everybody. Today's podcast was supported by the University of San Francisco and their new Master's in Applied Economics degree. So if you're considering grad school and you're interested in data science, let me tell you a little bit about why an applied economics degree could be the way to go. In the new digital economy, everything is about the platform. You know, I wasn't an economics major myself, but I did take a lot of econ classes, and I gained a strong appreciation for econometrics that benefited me greatly in my career. My understanding of the Vickrey auction helped me to work in search engine marketing, since most of the search ad platforms and many other platforms use auction mechanisms. And as the digital economy grows, I've been excited to participate in projects related to tracking of reputation, online experiments, and causal inference, and all the tools that are really affecting the decisions businesses make today. Not to be outdone, the University of San Francisco's new Master's in Applied Economics degree is also going to teach you machine learning using R and Python. This is a STEM-designated program, which I appreciate very much. And you can get an application fee waiver by visiting the link I'm going to give you. It's usfca.edu/skeptic. Once more, that's usfca.edu/skeptic. One of the things that I really took notice of when I first read the paper was the breadth of different NLP tasks you used it on, and how kind of remarkable it did without being specialized to those tasks on a variety of benchmarks. Could you talk a little bit about the empirical results that are shared in the paper?
The main empirical result we had was exactly what you said, is that we showed that these ELMo representations that you can train with a single pre-training model are transferable to a very wide variety of different NLP tasks. In the paper, we evaluated on 6 different tasks. These were things ranging from sentiment classification to question answering, information extraction, and then other more structured prediction tasks, things like co-reference resolution or semantic rule labeling. We also evaluated on a sentence pair classification test, natural language inference. What we did in these cases is we took what were, in some cases, the state-of-the-art system, in other cases were very strong baseline systems that were close to the state-of-the-art, and essentially did what I suggested earlier, is we computed the ELMo representations and then added them to these existing state-of-the-art systems, and in all cases got significant improvements in the previous state-of-the-art. The empirical result that we concluded from this is that these ELMo representations trained on a large corpus learn very useful, generally transferable properties of English, which is the only language we evaluated on. They're transferable to a wide variety of different NLP tasks. There's been a lot of subsequent follow-up work, some of which by us here at AI2, but also in the broader research community that has tried to answer the question of why are they so transferable, or what types of interesting properties do they learn as part of this unsupervised pre-training that makes them transferable, and what particular tasks are they most transferable to. But in the paper, we essentially just showed that they did improve downstream tasks and provided a very, a half a page or something of analysis to try and answer the why question.
And one of the novel features of ELMo is that it's a character-based approach instead of just a word or token-based approach. Can you talk a little bit about that choice and how it impacts the results?
The choice to use a character versus word approach was based on a couple of considerations. First, it was based on the consideration of wanting to build a single system that could process as wide a variety of different text as possible. And in particular, you would love to be able to make an informed representation for words that you've never seen before, based on things like the morphology of the word, whether it's capitalized or maybe with the prefix or suffixes or something. And previous work in language modeling had showed that by incorporating character information into the model, that the model is able to learn this to some extent. Practically speaking, what this means is that you don't have to worry about the out-of-vocabulary issues that you always encounter when you have, say, pre-trained word embeddings like glove. Now, there have been some other approaches to incorporate subword information, character level information, or other subword information into pre-trained word embeddings. So that had been to some extent solved. But in our case, we just took it as a convenient starting point that we were going to not have explicit word representations, but just character information. And the model then learns how to compose various letter combinations or into word representations.
I know this paper came out a few years ago at this point, and there's been research since, and a lot of things inspired by ELMo. BERT comes to mind, and maybe GPT-2 are kind of in the same family, if you will. Can you talk about the evolution of these architectures and where ELMo is going, maybe a little bit about where your research is headed?
But yeah, as you mentioned, we put the paper on archive over a year ago now. I would say probably the most significant thing that's come out since ELMo has been BERT, which extends ELMo in a couple of very interesting ways and also notably scales up the size of the training data set and the size of the model. So the various extensions in which it's been moved, we'll just talk about BERT in particular. BERT does a couple of things. The first is that it switches away from the recurrent neural network, the LSTM architecture that we had used in ELMo, to something that is based on feed-forward networks and self-attention, something called the transformer architecture, if your listeners are familiar with that. This is a much more computationally efficient approach, especially on specialized hardware like TPUs that Google has developed. And so by doing this, it allowed Google to scale the size of the model that was trained by many times. Since we're limited essentially not by the amount of training data that we have, because we have more or less unlimited training data, to some approximation, the quality of the resulting model that you get is tied very directly to the size of the model, essentially, the capacity of the model. And so that was one of the main contributions that BERT had, but also had several others. It changed the language modeling law slightly to one that instead of, say, taking a partial sentence fragment from only one side and trying to predict the next word or the previous word, it used this masked language modeling objective where, say, I'm just going to remove one word from the middle of a sentence and try to predict it given both the beginning and the subsequent context. And then the third thing that BERT did was that it showed how to combine learning both word representations that we do in ELMo with sentence representations, and then combining them both into a single objective loss by combining their mass language modeling loss and their next sentence prediction loss. All of these things combined contribute to having significant improvements over the ELMo model that we had trained.
Well, in terms of, continuing that momentum, we've kind of touched on, I think, the two major axes of potential improvement. There's larger corpuses and there's, maybe we'll call it, more clever neural architectures. Which, if any, do you suspect is the most fruitful avenue to be chasing down?
I think it depends on who you are. Certainly at the upper end of BERT large, the large BERT model requires a substantial amount of computation in order to train the model. It's inaccessible to individuals that don't have access to a large cloud computing budget. If you have access to large amounts of compute like Google and Facebook, the very large organizations, then certainly scaling the size of the model. I find it very interesting to think about. One of the interesting results of the BERT paper was that it doesn't appear as though the size versus quality curve has started to significantly level off yet. There's still a significant improvement between the BERT base model, and which is actually still quite large and still much larger than the ELMo model, but then the BERT large model, which is 4 times larger, there's still significant improvement. So it's an open question to me how far you can get by just scaling the size of the model. OpenAI's work, the GPT-2 that you referenced, gives some hint that as you scale the model size very, very large, that it keeps getting better. So I think that's a very interesting avenue for organizations that have access to substantial amounts of computing power. But I think that there's something missing from these systems, and I think that it's evidenced by the fact that they require a substantial amount of training data in order to learn quality representations, and in particular far more than humans do. I don't know what the estimates are. I've seen them, but I forget them off the top of my head. But the amount of words that a person might hear by the time they turn 10 or 15 and are fluent in a language or know a language very well is far, far less than the training data size that we're training these language models on. And so there's something about the data efficiency that says that they are significantly different than how humans actually learn and process language. And so what that is, how we get that into our AI systems is very much, I think, an open area of research, and anyone's guess is what the answer is. But those are the types of questions that I think would be very interesting to see the research community start to address.
Absolutely, yeah. Maybe to wind up, I'd love to go into maybe a little deeper example. You'd mentioned the Semantic Scholar one in passing. Could you share some details on that project?
Yeah, so the original project that we were working on that motivated ELMo was doing information extraction. The task that we were considering was one where you're given some text from a research article, and you need to extract the key entities from the article. So these would be things like what data set was used in the study, or what were the methods that were used for these types of things. And then in addition, you need to say that extract relationships between the entities. So you might say, well, we applied this method or this treatment for treating this disease. So maybe in the biomedical setting, the entity types you might extract might be disease and treatment. And then you want to say, okay, we applied this treatment for this disease, big relationships between entities. And there was a shared task that was going on. This was a Semival 2017 shared task that they had collected some annotated data and were running a competition for this. And then so we started working on this. I very quickly began to think about, okay, how do we leverage all of this unlabeled data? Semantic Scholar at the time had very large, the corpus they have now they've grown it significantly in the last few years. We had lots and lots of research articles that we had collected that we could use as unlabeled data to train systems. And so we began thinking about how do you use these large corpora of unlabeled data. And so then the project, sort of make a long story short, the project that eventually we worked on, we had something that was a precursor to ELMo that we included in our submission. We had first place in the shared task competition, and then components of that were then reused and repurposed and put into production in the production Semantic Scholar system that at the time was also being developed for the PubMed launch. For your listeners that don't know, Semantic Scholar is an academic search engine. It's similar to Google Scholar, although it extracts structured information and uses state-of-the-art NLP techniques to extract semantic information from the articles that it analyzes. But when I first started working on the team, they'd only covered computer science and neuroscience. And there was a big effort to expand to all of PubMed, which was a huge undertaking. And so parts of the original system that we developed for the Semival task entity extraction system made it into the production system that then now extracts entities. And it does a lot more than this. It extracts entities and then links them to ontologies and displays now the rich semantic information that you see in the Semantic Scholar application today.
Very neat. Well, I'll link to that in the show notes as well as the original paper. Where else would you recommend people follow up online if they'd like to know more about the project?
So if you're interested in just looking at the code and using ELMo and using the pre-trained models, then definitely go to the Allen NLP site or look at our GitHub page. Obviously, the original papers are a great source of background information. And then there's also been a wide variety of other content that's been published, blog posts and follow-up papers now that also provide good background information people would like to read more.
Great. Well, thanks again for your time and coming on the show to share all your expertise.
Yeah, thank you.